Okay, let's officially get started. You may notice that I'm recording today's lecture. This shows up at YouTube, and there will be a link in the class, and I'll show you the class in a few minutes. I'll show you in a few minutes, where you can, if you miss a class meeting or something, you can see what you missed. Or also for studying purposes, for review for the final, or for doing the assignments. It's helpful to be able to go back and take a look to see, well, what was that assignment? What was that thing she did? Kind of thing. So you're here for computer graphics, and for brand new people, I think you're brand new, yeah. No? Are you brand new? Yeah, and he's new. Well, he's the second class today, but he's new. And you're returning or new? New. All of you are new. So you're gonna get, you two are gonna be sick of what I'm gonna say because I've already showed you my website and stuff like that. But computer graphics is a little different. So what you're looking at is the syllabus for the course. What you want to do is jot down this URL. It is www.bhecker.com. BHECKER.com. This is where I'm putting all the course materials for the class. You'll be using the EMS to submit your assignments. This is where you're going to get your assignments from. Eventually, the EMS will have your assignments in it as well. We'll have the descriptions and everything. So if you go into the Fall 2012 link, and you go under Computer Graphics, which is the second one here. So I'm only teaching on Wednesdays at ITU, and I'm here from the morning till I have meetings after this. So if you want to catch me for anything, Wednesday's the day. I'm here like off and on during the week on the other days, but not like reliably. So I will always be here at lunchtime, and the other class ends at noon, so 12, 1, 2. You got a couple hours, or 12, 1. You have an hour before the class, and probably an hour to, well, you're going to have many hours today. So today's the day to catch me here. I actually teach at other schools too. I teach at Cal State East Bay, San Jose State. I teach at Menlo College. So I roam around to different schools. So.
Is there an email coverage?
There is. It's B. Hecker. Actually, just like this right here, B. Hecker. Ooh, look at that. The picture moves. B. Hecker at itu.edu. It may also be in the syllabus, but I'll find out in a few minutes. When you read through these course materials, you're going to be freaked out. Don't freak out. I'm changing the course. This is the course that I taught last term, or I taught it not last term, but the term before. It was in the spring, but it was geared towards computer science, software engineering students. We've opened this course up to digital arts students and business students, which means I'm not going to require the same programming skills that I required the last time I taught this course. Primarily what's going to change are these assignments. There are about 5 programming assignments. These are not the ones you're going to have. This week, probably tomorrow, then by next Wednesday, because of the holiday I didn't get enough chance to edit. But by the end of the week, by the next time you come here next week, you'll have brand new assignments. The assignments will not involve programming. No programming, which is why we only have 17 people in this class, I believe, because everyone thinks it's going to be a hard class. Well, the last time I taught it, it was a rather hard class, but the last time I taught it, we only had computer science students in here. So, different class. This one is towards business and towards digital arts students. All right, very good. Okay, so, which means it's the same subject areas. It's computer graphics, and I'll talk about that in a few minutes. But the skill level in terms of the assignments is going to be different. So we still have in here, I'm going to leave in here programming examples, and I'm still going to show you some programming stuff. You just won't have to write the same level of program. And you won't have to know anything about C programming in particular. Most of the assignments, I believe, are probably going to be essay-based or research-based. May also be some problem sets, you know, with some short answers or some multiple choice or something. There'll be some sort of an assessment. Don't think we're not going to have assignments. We're just not going to have programming assignments. Okay, so with that said, let me go over the syllabus. Because everyone who hasn't signed up for the course because they think it's going to be too difficult. Which, if they took it last term, it was a different course. So, what are you going to do? Okay, so the assignment description is a little bit off because it's geared towards C++. I'm going to show you C and C++ though. So you'll see it applied because it's really hard to look at computer graphics without looking at computer programming and the way it's implemented. And the focus of OpenGL. But we're not going to work with OpenGL, we're going to work with a higher level API. And I'm going to demonstrate to you all of the tools that we will work with. So it does not require a programming background. Okay, yes? Oh. So computer graphics. What are you taking this course here? You're going to look at an introduction of the principles of 3D computer graphic modeling. I'll look at the 2D and the 3D graphic models to explain what that is. Also looking at the concept of rendering and animation as it applies towards computer graphics. Focus will be on the underlining. No focus on underlining algorithms and no focus on mathematics either. Because you're not computer science. I'm going to assume that you're not computer science students, therefore I'm not going to hit you with a bunch of programming algorithms or mathematics. However, simple algebra is needed to understand some of the transformations, adding matrices together, looking at the XYZ plane, which is more geometry than I believe algebra. You're not going to be required to use any math, however, but an understanding of that might help you understand some of the computer graphics stuff a little bit better. But you can still get by without any math, actually. Just, algebra probably would not be a bad thing to be familiar with, but if you're not a math person, don't worry about it. We'll be looking at modeling transformations, not a math-based concept. The 3D geometric plane, not really math-based. It's kind of light geometry, light. 3D viewing projections, modeling surfaces, curves, solid modeling, illumination model, shading, texture mapping, visibility, algorithms, animation, physical-based modeling. Whatever makes, and this is the way I kind of think about it. So when you use a camera and you take a picture, you're getting a snapshot, you're capturing light, you're capturing shades, color, sometimes movement, depending upon what you're taking it of. You got an angle, camera angle, you have all those different things. We have the same concepts in computer graphics. So when you capture the graphic, we can add models for lighting, different types of lighting. So the course is actually nice for computer graphics, or for, digital art students, because it really does talk about real-life photography. Which is not to say digital arts is all about real-life photography, it's digital photography. Well, what is digital photography? It's adjusting light, illumination, it's casting realistic shadows on an object, In fact, these are the minor little details that kind of make something feel real or not real. As an example, if you look around the room a little bit, you see that the lights are illuminating this, and it's more of an ambient kind of light source. And what we're talking about is kind of things that we'll be looking in terms of lighting in the course is, well, what kind of light source is that? What is it doing? Well, you can actually kind of see if you look at the walls. Usually, from my angle, I'm looking behind me right now. I can see a shadow, a dark shadow on that back wall. And I can see kind of patterns and shapes on the walls, and I can sort of see this part of the right is a little darker than the part on the left. This is what brings realism to computer graphics, to a picture. So we create this on the computer. So if we create, and you see some really bad games and some really bad graphics out there where there's no shadow, there's no cast, there's no rendering of anything, so you see everything's the same color, white walls. And you see, oh yeah, it's just illuminated because it's light in color. And it adds essentially, it makes a scene that's not realistic, doesn't look real. So then there's packages and applications and programs and things that allow you to make those settings to make it look real. Add a light source, add multiple light sources, change the camera angle, change the focus, change the perspective. Those are all the things we're talking about in the course. So the course is going to be, this particular course is going to be heavily focused on computer graphic techniques. so that you can pick up a tool set if you have an interest in picking up a tool set, and know that, you know, it's diffused. Do I want to put diffusion on? Do I not want to put it on? You know, and be familiar with some of the different settings, some of the different libraries for some of the different programs, if that makes any sense. So it's heavy duty into graphic concepts as they apply towards computer graphics. There's a couple of different web libraries that are as easy as plugging and playing. It's as easy as dragging and dropping stuff on a canvas that we'll play with. It's not programming. It's making a world, making a scene out of something. Hello? Oh.
Hi, I need to look out.
Okay. Right now, or?
No, not now. I need to ping us.
Okay, hold on. Let me pause this then for a second. Resume. All right, so we're back. So I was talking about concepts of computer graphics that we're going to be going over. So it's going to be mostly concept-based. I will talk about texture mapping, which is actually kind of a cool concept as well. Taking images, pictures. As an example, you have a picture, let's say, of some wood, and then texture mapping, it means put it on top of an image. Sort of like I'll talk about wireframing too, but it's kind of like wireframing something and then covering the surfaces with these images. And then mapping it so it looks very real. I mean, you can create a hardwood floor out of a piece of wood, picture of a piece of wood. Actually creating the floor out of it, which is actually kind of cool. Because then you can, if you're doing that, then you can make it so boards on the floor can come up, you know, for games and stuff, or that the floor moves, or something interesting can happen to it. So that would be part of animation, actually. So we'll talk about the world in terms of a graphic world, and objects in the world, the plane that makes up the world. I will also be discussing concepts associated with building and designing. I don't consider myself a good graphic artist. I am terrible. And most of my terribleness comes with my sense of color, actually, and I don't have the patience. So I'm a computer science person. So I know the concepts, but I'm not going to talk very much about UI, user interface, or design, although I'm pretty good. I mean, I wouldn't consider myself bad. I'm just not, I would not sell myself to a gaming company to do graphic art for them. I'm not of that quality. So there are some people in computer graphics that are graphic artists, and they are artists. And some of them lack the fundamental information. And then they have people like me who are the opposite. We have the fundamental information. I can make it look real, but I will have god-awful color choices and contrasts. And I know the right rules, but I just don't apply them because I don't think it looks good, or I don't have that natural talent. So, which is kind of interesting because you get all types in computer graphics. Usually if you have the natural talent, and you learn the technology that's associated with it to make it work, then you're extremely marketable. There's a lot of people out in the industry that don't have any natural talent, but they know the skill set. And then you get mediocre games, and then you get some really fascinating computer graphics and some really nice games. Those guys have both. Those have the artistic talent, and they have the technical background that goes with it. So I truly believe that there are two separate components. It's like you can lead a horse to water, but you can't make them drink. So you can teach me all, and I can learn anything there is about computer graphics, but no way in the world can I put together would I even have the patience to put together a Pixar movie or something. And that's all computer graphics. And we'll look at techniques for movies, for games, because some of them there's a little bit of overlap in concept. Because there's a lot of rendering concepts that are similar. But primarily it's an overview of a lot of different concepts. This is really considered Computer Graphics 1, or it's the basic, you know. What you should have when you get done with a computer graphics course is a basic understanding of computer graphics and some familiarity with some of the libraries and packages out there, and then some of the techniques used in developing programs with it. We're not going to write the programs, but we'll see it being used. So, focusing a lot on OpenGL. You might be wondering, why OpenGL? It is still the de facto standard. We won't work directly with OpenGL. My last class actually did. But we're going to work with packages on top of OpenGL. So, OpenGL is I'm going to explain right now. is a low-level library that works with C. It's a function-based library. If you're familiar with C programming, we have printf, scanf, we have a bunch of functions that we run. You don't have to worry about programming, and if you don't want to listen to this, you don't have to. This is above and beyond the scope of this course. But OpenGL is a library that you would include in your C or C++ program. Primarily, it works with Java though as well. And you'd make function calls and you'd do low-level building of graphic objects. So you'd create a sphere, you'd put the sphere together, you would give it, you would you'd create programs from a programming perspective, calling this built-in functionality that creates these objects and works with graphic libraries. Now that's the low-level base. Now we have libraries that work on top of that. As an example, there's a library built for Objective-C that works with the iPhone. So you can create an OpenGL project on the iPhone platform or on a Mac platform for that matter. And it's making higher level calls that are putting together the lower level details. So one API call from that package is like 5 OpenGL calls. It's a higher level language that gives you easier abstraction, easier to work with the language. It's like the difference between programming an assembly language and programming with HTML and CSS. You know? It's different levels of abstraction. Some languages are easier than others. So OpenGL is usually the underlining toolkit for all of the higher level APIs. It's all OpenGL based because it's like, well, it came from Silicon Graphics originally, but it was made to optimize the rendering process to work faster on modern day computers. So OpenGL is the foundation for the iPhone graphics, Android graphics as well. We have graphic libraries in Java that work on OpenGL. We can actually program on OpenGL with Java. We can program with OpenGL in C and C++ too. So, but you don't have to program in OpenGL. API stands for Application Programming Interface. So, if I had an API for OpenGL, I can say, give me a teacup. There is one that actually creates a teacup. And you know the Pixar, you remember the original Pixar animation with the lamp? I actually have one written in OpenGL that I'll show you in this course that casts light from a light source. It's a pinpoint light. And it takes the light and the lamp head moves around. Well, we have a lamp in an API. Without the API, without the higher level application programming interface, I could say, new lamp, new teapot, give me something new, right? Instead, if you were just using OpenGL, you'd have to put the pieces together to create the lamp, or to create the teapot. So what's the lamp? Well, we have a cone with a light source, with probably a rectangle base, perhaps, that's connecting to a long cylinder or another rectangle piece that has maybe a circle base on the bottom that is maybe 2 circles actually with a cylinder, or maybe it's a cylinder, small little cylinder.
Disk.
A disk, yeah, it could be like a component. And this is like one of it, maybe about 15 different components that make up this concept of the lamp. If you were programming it in OpenGL, you'd create every one of those little things. If you were, in fact, maybe, you know what? I think I actually have, I don't have it loaded on this computer. Next Wednesday, I'm going to bring in some OpenGL examples. I have to load the software on this computer. And I'll show you this, and I'll show you how it's constructed. I have a humanoid, it's a robot. Imagine non-computer graphics. You're going to create a real-life model. You're going to create the lamp. Or you're going to probably can make a lamp out of a coat hanger, maybe. I don't know. Or pieces, wood. Probably. Let's say you're going to build it out of wood. All the different shapes of the wood that you'd have to cut and make and glue together, or, I don't know, use nails or screws or hinges or something to put the thing together, you're doing the same thing on the computer. If you're using OpenGL, you're making all those little pieces. They're different shapes that you're putting in a plane, XYZ plane. So you're putting one shape on top of another. As an example, if I was going to build a humanoid, I can have a rectangle for the forearm, a rectangle for the upper arm, and then put like a cylinder or put something in here like a hinge kind of thing to make it move for animation. Because if I didn't do that, if I just made it one, my arm would go like this. So some of the computer graphics is done, the smaller the components, the more animation you can apply towards it. So if I had a wrist element in there too, I have 1, 2, 3 components, let's say, for example, which is what I would do if I was creating a humanoid, then I'd be able to move the hands as well as the forearm, as well as the upper arm. Which, on the lamp, which was actually kind of interesting, the intricate details they had, that little thing that moved, and it was smooth. So most people, they look at that and they go, oh, it looks like a lamp. Well, the thing is, at the time, it was like way advanced. And then the light source moved, which was interesting. Because, how are you going to achieve that? That was done in OpenGL, by the way. Hey, how are you going to achieve that? That was like the start of OpenGL in terms of the graphic library. But that's like about 15, 20 different components all put together to get that kind of movement out of that. And then the animation is moving items around the plane. So we have the 3D plane, which is X, Y, Z, 2Ds, X and Y. We add the Z component, which gives us our back and our front essential view, which means we can turn the object around now 360 degrees. It has a back side, a front side, a left side, a right side kind of angle views, which is the same thing you get in photography if you're working with 3D. But photography right now is still just 2D, isn't it? It's two-dimensional photography. But so you have higher capability. I believe you actually have higher capabilities in terms of graphic capabilities on a computer than you do with modern day. But we have digital cameras now, so I don't know. Once you start making it digital, then you can capture a lot more information. So we have rendering that happens of this image, and then we have transformation of the image. Transform an image means to move it throughout the plane. And then we have things like back-facing, forward-facing, rendering, which would say, let's say for example we had me, and I was on a computer. Can you really see my backside right now? It would probably be hollow if I were on a computer. But if I turn around, then you can start seeing images of the back, and I would fill it in. That's rendering. To fill it in, would be forward, back face. Back is empty. Well, why are you going to render it? Or are you going to render it last? So you look at, there's computer graphic techniques to look at the scene and say, well, what's the starting position of the scene? Render that first, and then you work with the back. And then there's techniques for computer graphics that you can use to minimize the amount of memory you need. As an example, if I were trying to minimize memory, I wouldn't have a backside, I'd be hollow. I'd have, and you actually see games like this. All of a sudden, they like the animation, the guy moves over, oh, but he's hollow. Or I'm sure everyone has seen this on some antique computer game before they started getting sophisticated with this. Because really, amateur graphics, you're not going to think about stuff like that. And then the guy's going to move and all of a sudden it gets black. You see that with movies. Actually, Roger Rabbit? The animation, there was one point where there was a hole in the arm. They left it in the production. They didn't find it till after. It was like a split second. It's like it didn't render fast enough or something. It was animated characters that was mixed in with humans, and it was a combination of film and computer graphics, and it was overlaid. And apparently, one of the computer graphic images was partly rendered. It didn't sync correctly. Part of it was corrupted or something. So you had like a black hole, like a black spot, but it like happens for a second. And then your eye's not, sometimes your eye's not going to catch it either. Depends on how many frames per minute is up there. There's a lot of garbage. Because your eye can only see a certain speed. And if it's faster than what your eye can see, you're not going to see it. Or you're going to see it like once in a while, but you're not going to see it every time. It just happens to be the way your eyes caught it. But it's actually even in regular old film that happens. It's when you get corrupted, especially in digital. You're not going to get this in the old-fashioned film, but as soon as we got in digital, we have mix and matched pixels, wrong shades of pixels, lost pixels. You get this all the time on digital cable. how many times do you really see it, and then you look at it and go, you know, like, oh, I saw something. I mean, I'm sure we've seen black squares, usually, because now our pixels on digitals are squares. Well, most of them are squares. We're looking at Comcast as an example of this. So the image is coming in, you see, but are you really going to notice the black missing square on a background of something? It's usually only when it's like showing you a picture of the sky, and then you say, what's that square? Oh, lost pixel. And then that's not necessarily in the image, it's in the transmission of it. So it didn't make it to your system. But actually what they'll do now is they'll just scramble the whole thing. So it'll just look like a mess. Because don't take part of it if you can't take the whole thing, because it's not going to look right. So. But anyway, that's a graphic concept. That's a rendering issue, actually. So it's rendering is producing the image. So we have graphic cards, and I have an entire lecture on hardware, actually, that I'll go through. But we have memory on these graphic cards. We even have GPUs now, graphic processors. So your computer has a CPU. Well, you can have a graphic card with a GPU, graphic processing unit, that's going to do all the processing. Like, what kind of processing could we possibly need? Well, computer graphics would be great if it were just images. Two-dimensional pictures, you know, that we took from our digital cameras and we put on the... No, even those images take a long time to process, but what we're talking about is rendering. And the rendering needs its own processing. I'll talk about the rendering pipeline. I'll talk about rendering concepts in this course as well. Rendering we actually hit pretty soon because it's kind of a base concept. What does that mean? It means actually drawing out the image, filling in the details of the image, and then applying the light, the shade, the color, all these components that are associated with the image. I'm doing it in real time. And then applying animation to it. Which is why in the old days we had video games that were kind of slow. And or things that move kind of, or the audio doesn't sync up with the video correctly. It's usually because you have a really bad graphic card on your computer. You can actually experience this, no problem. Take an old PC, hook up a DVD, high definition DVD to it. That processor's not going to render that thing fast enough. Instead you go, it doesn't move correctly because it's trying to render the image, process all the data that's associated with what it's reading, and put it out on the output for you real time while you're watching it. So usually you can put a buffer on there. And so some graphic programs work with buffering that the API will give you. It'll create the buffer for you. It'll put the graphics in the buffer. Because if you can't build the whole thing simultaneously to watching it and viewing it, then you buffer it. So most of your graphic TV capture cards buffer it. So if you play the TV on your computer with one of those little graphic TV playing things, and you go and turn on the real TV, like the regular broadcast signal, there's like a 5 minute, oh not 5 minutes, there's a 5 second delay or so between the two of them. So one of them will be slow. The buffered one will be slower. What does that do? It takes all the stuff, puts it into memory. So now we have graphic cards with memory on them. 512 to actually 1 gig is pretty decent right now for memory on a graphic card. What do you need that for? Well, to hold all the graphics you're using. But if you're not running any programs, which is kind of ridiculous because consumers don't know this when they buy computers, if you're not running any graphic intense programs, what do you need graphic memory for? What do you even need a GPU for? So a lot of it on the consumer products, a lot of it's shared. So your 4 gigs of RAM will be shared. Like a 1 gig of it will be, or 512 of it will be dedicated to the GPU processing, and the rest of it will be available for the computer. So you see it on the boxes. It says shared video RAM, And then sometimes, in notebook computers now we have the graphics built onto the board instead of it being a separate card. In the old days when this stuff was still starting out, people would go and buy graphic cards. Put the card in there, and a card would have its own GPU on there. It would actually be like a computer inside of a computer, just for rendering, just for making those graphics work. So things have grown a lot significantly, especially with the speed of hardware, speed of CPUs, memory. So it's a lot fascinating, actually. Now we can put this all on a mobile device, run it on an iPhone. Get really good rendering. In fact, better rendering of a DVD on an iPhone than it would be on an old computer from like 5 years ago. Which is kind of weird. Actually, if you think about it, your mobile devices are running faster than computers. If anyone remembers the old 386 or the 286, the 8088s. Yeah, those chips, those speeds. Oh my god, it's so slow. Your mobile phone runs 10 times that fast. Actually, there's some mobile phones that run faster. Dual processing with some of the Google phones run faster, and tablets run faster than computers do. Technology is just great. Alright, so enough about technology. I'll have a lecture on technology. Actually, that one might even be 2 weeks away. That one's pretty soon, actually. It comes happen after the overview stuff. So this is going to tell you about matrix algebra. There's a little bit in there because you need that for transformations. In order to move something in the plane, to move it left, move it right, up and down, you kind of have to be able to figure out what the coordinates of those components are and then take the coordinates and adjust them. And we're just taking and moving it 5 pixels this way or 5 pixels this way or something, which is how we're transforming the image, and we're creating animation out of this, which is what we're looking at in terms of 3D. So the 3D plane just gives us the extra back and the front kind of thing that we can kind of look at. We can turn the object 360 degrees around. We're still seeing it on the 2D display, however. This is not a 3D display. Computer graphics and computer monitors are two-dimensional. So we're taking three-dimensional and we're showing it on two-dimensional. Well, it's the rendering that's giving us the three-dimensional. I heard there's a computer display. I saw a commercial for it the other day where you can put on the 3D glasses and you can see your computer in 3D. You have to have the right monitor for it, though. I mean, the right display in it. I think, is it HP or something? Someone has come out with this. I'm thinking, why do you want to wear glasses, though? To look at your computer. Actually, your 3D animation, which is really popular right now with the movie industry, they've actually made it so it's really nice because it's not as fuzzy. It's almost 4D at this point because it's not as fuzzy. It's higher quality, which means if you don't wear the 3D glasses, your eyes can still pick it up. Your eyes can still focus. You can still see the 2D image correctly, with just slight imperfections. So it's like a transformation between combining the two, making it so that the 3D doesn't detract from the 2D view. So, which is kind of interesting. It'll be interesting to see what happens with that in the future. It'd be nice to be able to go into a movie theater, right, and put on a pair of glasses, watch the same movie as somebody else without glasses on. And the glasses, which is what they're striving for. Because I don't like to wear the glasses. And I don't like 3D movies because they're stupid. In the old days they were really stupid. It's like, yes, the plane is flying out and hitting you in the audience. You're like, well, why? And they'd hold out the little snake or something, the rat or something, because this thing was coming at you. Now they're not doing that anymore. Now they're just like creating. But who needs 3D? I don't know. I never got it. I was lost on it completely. But then again, I told you I'm not an artist, so I don't appreciate that. All right, we'll talk about 2D and 3D. So here's our learning outcomes after completing this course. Knowledge of computer graphic concepts, including 2D and 3D. Yes. Geometric and modeling transformations. Yes, that's a big point right there. Understanding image formation and representing knowledge of, of formation and representation of images. This is what we're going to hit next week, actually. We're going to hit both of these two next week. And knowledge of OpenGL, okay, not so much knowledge. We'll use web. I have to actually do some research to see what is compatible. I want to use open source software that's compatible on both the Mac and the Windows system. Because I know some of you guys have Windows systems and some of you guys have Mac systems, and I want to make sure it's compatible. OpenGL is compatible on both, and that was no problem for the last time I taught this course. However, if I'm going to go higher up in the APIs, I'm going to have to decide on something that is going to be a good compromise for different systems. So you may use any computer you want for this course, Mac, or you're going to need a computer. Oh, also the other thing too is next week I'm going to have tables in here. So For the computer graphics class, you're not necessarily going to need your computer every week. Hopefully I will tell you in advance what we're going to do. For the other class stuff, for HTML, CSS, you're probably going to want to bring your computer. So this does not lend itself well to using a computer. So I'm going to have tables in here so you can actually have a place to sit. Like you guys are comfortable over here, but if we actually get 17 people to show up, they're not going to, we're not going to have spaces for everybody. So we get some comfortable seating at least. Okay, so knowledge of the scan conversion methods, projections and viewing, understanding texture mapping, modeling of curves. So the curves are actually kind of funny. Surfaces are funny. The different surfaces, textures. And a lot of stuff you guys have seen before. You know when something looks shiny, or when something is ultra shiny, or when something is slightly shiny, or something is matte. So, but how to achieve this in computers and when to put something on, something like that. It's a combination of all these different things that gives us a real picture of what it is we're looking at. Because imagine we were mimicking the real world in a computer program. So we're trying to get realism, and it's unfortunate though that I can break down, and you'll be able to break it down too, realism into components. And then you think, well, what part of life is really artificial intelligence? It's like, oh, that's really life in general. I mean, I could make this room unreal completely just by taking out all the shading. Changing the light around. Maybe that's why people look better in the dark. Because you can't see them. Not a computer graphics concept, however. It does lead into the artificial intelligence kind of concept. Alright, required textbook. I don't think anyone's going to buy this book. I have a copy of this book. I should really put the word recommended. The book is actually kind of expensive. The book is like $150 to $200. However, it's definitely the Bible when it comes to computer graphics books. And it's all on OpenGL. There's one that's called the Red Book. In fact, it's down here. Where's the Red Book? Well, it's not called the Red Book on here. There's some optional books here. Don't run out and get any of the books. Especially, they're all related to OpenGL, by the way. And I just told you at the beginning of the course, or the beginning of this lecture, that I'm not going to do OpenGL for this class. So, what doesn't make any sense. So, I should really edit this syllabus, take out the books. So, I will let you know as we go through the course electronic stuff. So, and it depends on the API that I look at in terms of what we're going to use. Until I decide on what we're going to use, I can't put a book together. And the assignments, don't look at them either because they're all OpenGL. So I have to change those as well. But next week we'll have everything set. So don't read the stuff about the book. You don't need the book. What do you need? This format's going to stay the same. We're still going to have a final exam. We're still going to have a CSLO essay. We're going to have some assignments, and we're going to have a midterm. No changing of any of that stuff, which is great. Because I sort of like this format. Alright, what does this format mean? So, we're going to have an in-class final exam. We don't have a final exam week here at ITU, although we probably should. Hopefully we'll have one in the future, but I do my final exams the last week of class. I believe in the schedule they usually have final exam week, but like we're Wednesday, so it'll go like Tuesday through Thursday. Like what happened to Friday classes? What happened to Monday classes? So just think it's probably going to, and I'll announce it as we get closer, and I usually hold what's called a final exam review. And the review is going to tell you everything that's on it. So if you show up for it, you'll ace the final exam, no problem. And final exam is meant to be an assessment that's in class. Also, we have this thing called a CSLO. It's an essay that you're going to write. Because we're a graduate school, and we're supposed to have, a lot of you go, well, most of the students right now are international students from different language backgrounds with different English comprehension skills. This is your one opportunity in the entire computer science course, or digital arts course, to express yourself in writing. So this is your opportunity. In fact, I can bring up the CSLO essay because I don't believe this is going to change at all. I have to take a look at the topics, so I might actually have to adjust it. And we also have a take-home midterm. I'll look at that in a few minutes as well. But the CSLO, let's talk about what that is. Here it is. What is a CSLO? Well, let's see. Zoom this in a little bit. You're going to select one of the following topics. You're going to write a 2 to 3 page paper, double space. So that's really 1 to 1.5 pages that you have to write yourself. Your own words cannot contain portions that are cut and pasted from the internet or any other sources. Has to be your own words. Yeah, I think students in the United States have learned how to write by cutting and pasting from the internet. It's not just international students. Seriously. They cut and paste from the internet. You can tell because even the fonts are wrong. At least change the fonts so the whole thing matches. Sometimes it's like 10-point font, 12-point fonts, different ones. Oh, come on. It's supposed to be a graduate level course at a graduate school. You're going to get a master's degree. At least learn how to write. Alright, so you're going to write a 2 to 3 page paper that's double spaced. You'll thank me for it further down the road when you write a report. I don't know how to write. Is it on the internet somewhere? Alright, so I might adjust these topics. When I have everything ready, I'll go through this again. But you'll have to pick one of these topics. These topics, I believe, might be a little too complicated, but we'll see. I have to review this stuff. But you're going to pick one of these topics, a topic of your choice, and write about it. And it probably is going to require some research. Because unless you know exactly what rendering pipeline is, you can get some of it from the lectures that I'm going to be giving you. But other parts, you're probably going to want to go to the library or go online and find some books or ebooks or something or some information. And just put it in your own words when you write the paper and then cite your references, essentially. You're going to do a little bit of research, learn about the concept. It might be interesting, actually. Yeah, you get your choice. You only write one essay. It's on one of the topics that you're given. So it's not too bad. The midterm for this particular class is a take-home midterm. So here's the midterm. It's take-home about halfway through the course. The CSLO is a take-home assignment as well. That's the essay. The final exam is 25%. It's in class. That one you can't get take-home. That one's required. And then the assignments, well, there's only 5 of them. They're going to be hands-on. Don't look at those assignments yet, though, because I don't know what they're going to be. It's only 25%. So majority of the grading is on the final. It's on the CSLO. It's on the midterm. So we'll take a look at the midterm. I might actually have to redo the midterm too, but we'll just take a look here real quick. I think the midterm that I used last time, and it's going to be recycled. Well, probably not actually. I'm probably going to come up with a new one as well. But I usually like to keep the same format. And I just change the questions around. So the CSLO will be the same format. It'll just be different questions, different options that you can pick from. That will be easier options. It might actually be more art located versus computer science centric. This one here, you're just answering questions. It's a pretty easy midterm, actually. This midterm will be changing as well because there's questions on OpenGL and C++ in here. So I will need to give you guys a different midterm exam as well. So this midterm is going to change. So don't follow any of the assignments or the midterm or even any. Next week we'll have brand new stuff for everything. So let's see. So it's 25, 25, 25. The LMS is used for uploading assignments. If you go to lms.itu.edu, this is what Doreen, the person that was here earlier, was asking. Some people are having my big picture. Some people are having a problem. I wonder if this one moves. It does move. It's just really weird. It's bad graphics. If you go into your courses, you'll see, but the class will be empty right now. If I go into, which one is this? Computer Graphics 1. Your interface will look slightly different than mine. And this is all 0, 0, 0 right now, which means I don't have anything in here. So what are you going to find in here? You're going to find in here the lectures, the PowerPoints. You're going to probably find a portion of the recorded videos. However, I have another website, which is out here, YouTube/bhecker. I will put links to the videos for this class in the class that's on bhacker.com in the forum kind of interface, so you can just quickly link on that. Or if you get bored and you want to watch videos, BJ Hecker. J is my middle initial, stands for Jill. So B Hecker was taken. There's another Barbara Hecker or something out there. So I had to go J, had to put Jill in there. So now you know my middle name, BJ Hecker. So, although I recently discovered that wasn't such a good choice either. So, but I won't tell you why. I've already been informed by a couple of male students, actually, who had a comment on that, and I'm like, no. Because you know what, well, okay, now I've gone it, I've done it, I've gone that far. I said, BJ, like, it doesn't stand for that. Right, might be an English thing, so I won't enlighten you on what they were saying with that, so you can just imagine. Oh, good! Well, okay, I'll tell you what, okay, do you know what BJ stands for? Okay. So, but I know, I'm like, well, it stands for Barbara Jill, that's what it stands for. Anyway, oh, that was a terrible name. Oh, just Bridget Jones, there you go, that's another BJ. So, alright, so, I'm leaving it. I'm not changing it. I've had it for over a year. I'm not changing it. So, alright, so enough on that topic. So academic dishonesty. I hate to tell you, but and it's a sad reality for ITU. But we are getting our stuff together. There's no such thing as cheating anymore. However, we have had some batches of students that have come through this university who have rampantly cheated and plagiarized on practically everything you could possibly imagine. Not tolerated. Not being tolerated. So, best if you do your own work. Don't copy something. If two students turn in the same piece of, and I say this every single first day of every single class that I have, and yet I still have students who come back, but there's no buts. If somebody else turns in the same work that you're turning in, you're not going to get any credit for it. And it's just not just me, it's everybody. It's the entire university. Same thing applies towards attendance. And you see, there's nothing in the grade on attendance. I don't grade on attendance. However, attendance is required. In fact, the rule now is 70% attendance, which means you can miss 30% of the class. So it's unrealistic for 100% attendance. But if you're CVIS students, if you're an international student, we abide by CVIS standards and CVIS standard once, I think 70% or something of that nature. I don't work in admissions or registrations. I don't know, I'm just told 70%. So that's why we have to take attendance, and it's kind of like high school, but because we have some students who don't show up. Like, for example, we have 17 students in the class, and I got 1, 2, 3, 4, 5 students sitting here right now. So the rest of them are going to get in trouble for not being here, which is sad, actually, because at the end of the quarter, or semester, I should say, when the grades come out, they won't get a grade. And then they'll go, well, how come? I don't make the rules. CVIS makes the rules. And WASC is making our rules when it comes to academic dishonesty. We can't have two students turn in the same program. There's no group work in the class. There's nothing that should match. And if on the CSLOC, which is the most important part of it because it's a writing assignment, you can't cut and paste it from the internet. And I already gave you guys earlier my Wikipedia story, and if you know, it's just not worth it. Just because if you do something that's yours, you're going to get a pretty decent grade for it. Because right now, your competition is pretty low. Because if you're actually doing your own work, you're a straight A student. If you're not, you're an F student. So anyway, I'm trying to encourage people to do their own work. Long story short, that's all I have to say about this academic dishonesty. Let me talk about the grading formula for a few minutes. There are some teachers at ITU that give out A+. I don't know why. I wish they would just take it out of the options, because there's no such thing as an A+ at ITU. It doesn't count for anything higher than 4.0. An A+ and an A are the same thing. You can't get past 100% in a course. You can't get past 4.0. It's not like high school. So, when you had, you know, AP courses and you can get pluses, which was what, 4.1 or 4.2 or something? I don't know. Anyway, long story short, an A is the highest grade you can earn. whether you get an A plus or an A, it's still the highest grade you can earn, grade point average. And I do give out pluses and minuses. This is pretty standard actually for last term. This is actually a D, but in fact last term I raised this 10. This is what it used to be 50. See, 50% for a C, but there's some people got below 50%. But this grading is pretty standard. This is a graduate level course, which means if you get a C, you didn't really pass it. A C in a graduate level course is a D. Yeah. You want an A or a B. You want a 3.0 to graduate, which is a B. So you don't want a C. If you get a C in a course, it really means you failed it or you got a D. But it doesn't disqualify you for OPT or CPT or I don't know, unless you're average. Unless your total GPA is too bad. Don't talk. I'm not an expert on GPAs either, so don't ask me about GPAs. So you're not going to get below a C if you've done your own work and you're above a 60%. I'm not going to give anyone a D in this course. Hopefully, you're going to be right here in the A range or the A minus range. So what are you going to do in this course? Well, let's see. Here's our course schedule and assignment due dates. I don't have any assignments yet, so I don't have any due dates on these assignments yet either. But I will be doing exactly what I've been doing in my previous classes, which means everything is due on the very last day of class. So don't be stressed about the schedule at this point. Although I did kind of stretch it out. We will have 5 assignments. The midterm should probably be done in the middle of the class, around week 7-ish. When the midterm is ready, actually next week I'll be going over everything. But again, when the midterm is ready, like a week or so, I'll say, hey, you should be working on the midterm. And then I'll answer questions and preview the midterm for you. Not going to be a programming assignment. It's going to be a short answer kind of thing. It says in class, but don't worry about that. It's not in class. I need to edit this syllabus, actually. Because I need to change the description, take out all the OpenGL stuff, too. So this week, which is today, we only meet once a week on Wednesdays. And we'll probably go from 1 to 3-ish. We're supposed to go from 1 to 3:45. Especially if we have a small class, it'll be fun. I can get through a lot of stuff really easily. And if that's the case, we'll go from 1 to 3-ish. So, which is nice. I rarely go past 2.5 hours. Sometimes we'll get out later, sometimes we'll get out earlier. I'm really supposed to hold you for 2 hours and 45 minutes. No. Not exactly. Maybe on the final exam we'll stay that long. So reserve up to about 3 o'clock. That's what I'm saying. Rarely will I let you out later than 3. Like right now, it's 2 o'clock. So we've been going an hour so far. So in regular class, I might have a little bit more. I might have 45 minutes more or so. I'm going to end actually pretty soon, but today's easy because it's the first day of class. But once I start getting into the lectures, it's going to take a little bit longer. So, all right. So next week, which is week 2, we're going to get into chapter 1. This is going by the format of an old book, so I probably should take out chapter and replace that wording with lecture. Lecture 1 is going to be on graphic systems and models, 2D, 3-dimensional. Getting and learning the vocabulary. It's the vocabulary lesson. Lecture 3 is going to be on graphic programming, but it's going to be on the introduction to the APIs and I'm going to kind of rig assignment number 1 in relationship to an orientation to the tool sets. A kindergartner can do this stuff. It won't be like difficult stuff. So don't worry about the programming part of it. We'll also look at, and then basically think of these as subject matters. We'll get into input and interaction. I'm probably going to hit hardware in here. It's not on the menu here, but I'm probably going to hit, just an orientation to the hardware. Just, because some of the terms are hardware oriented. And the concept of the pipeline, the rendering pipeline, which isn't even in here. So I might actually modify the subject matter a little bit in terms of when I edit this syllabus and kind of change the topics so they're more reflective. Because basically I'm remodeling the class. I'm taking the whole class and transforming it. So And you're seeing the old syllabus is what you're looking at, the old materials. So once I have this done, I'll go through it again with you and show you the format kind of thing. But it kind of, most of the stuff's going to stay the same. I'm probably also going to substitute some of the lectures. Some of the lectures in here, let me go back to this. This is the old archived class that was taught last term. You'll see the video lectures for it in here, and you'll freak out. Some of them are a little bit more above and beyond what we're going to do in this class, so don't freak out. Instead of you hit it on the lectures here, you're going to see a lot of 1As, 2Bs. There's like, oh, I don't know, there's like 50 lectures in here. I'm not going to hit them all. This is like my repository lectures, so it'll be topic by topic, which is why I have the final exam review, because then I'll tell you which topics. Because by the time 15 weeks is over with, some of you are going to be, what in the world did we cover the first week of class? I have no idea. Or second week of class? So, most likely a lecture 1 and 2B. I don't think I'm going to cover 2A. You know, some of it's on OpenGL, and if it's on OpenGL, don't worry about it. I will cover OpenGL just as a topic, because I think it's worthwhile, because a lot of our graphic packages are based on OpenGL. And I'll show you OpenGL examples probably as soon as next week. I have to set my computer up though. But you won't have to program in it. What did I forget? I have no idea what I forgot. This is basically just the introduction to the course today. So what do you want to do for next week? Well, what do you want to do for next week? There's really no homework in this particular class. Nothing you really have to prepare for. Actually, no, there's nothing really you can prepare for this class. So, so for next week, just show up again. And that's about it, really. So, did I miss anything? You guys have any questions? How's that? Questions are always good. Don't worry if you don't have LMS login access. Don't worry about that yet, because there's nothing in there. There's nothing in there for you to see anyway, unless you're taking another course, which they might. Nobody's got anything in there. Are you kidding me? The semester just started yesterday. So everyone's still getting their materials ready. No, if we don't have any questions, then we're going to be done for today. If you came in late, I think you still need to sign the roster. Yeah, I can stick around for questions, comments, nothing. Just rest up, enjoy your week. You know, come here next Wednesday, 1 o'clock. Okay. Thank you for showing.